So, good afternoon, everyone, and welcome to today's live webinar on quantum sensing with NV Center, a live educational demo hosted by Digito Technologies Private Limited in collaboration with Qutools. I am Rinalini, working as solution engineer at Digito Technologies Private Limited. So, welcome you all, and we are pleased to have Slava Tazanova from Qutools, Germany, as our resource person for this session. Today, we will explore both fundamentals and practical session of sensing. So, I will just introduce about Digito Technologies. So, Digito Technology Private Limited focuses on building um, industry-ready engineering ecosystem for academia and research institutions. We accelerate prototyping, experimentation, and deployment through cutting-edge solutions in test and measurement, FPGA hardware, 5G and 6G, wireless testbed, edge AI, and quantum technologies. Talking about the key solutions which we offer. So at Digitode, we provide a wide range of emerging technologies, including automated test and measurement solution for high performance real-time monitoring, edge AI and machine learning solution for real-time embedded intelligence, FPGA-based design, verification, and prototyping, 5G and 6G wireless testbeds for next-generation wireless technologies, quantum and optical solution for quantum communication, fiber optics, and photonic devices. Talking about our collaboration, at Digitode, we work closely with leading global OEMs to deliver end-to-end educational lab and research solution across emerging and core engineering domains. With ST Microelectronics, we provide edge AI and embedded AI solutions. With Digilent, we offer a wide range of solutions, including FPGA development boards, analog discovery modules, and USRBs. Through Qutools, we deliver advanced photonic and quantum technology solutions. With Mantis Wave, we enable private 5G network solutions, including network in a box system, multiple use case labs, and RIS system. In collaboration with TMY Tech, we provide 5G and Wave testbed solutions supporting FR1, FR2, and FR3 ranges. With Crobot, we offer mobile robotics solution focusing on autonomous navigation, sensing, and real-time control applications. Through QBRID, we support quantum computing education, enabling listeners to access quantum programming platforms. With Emona TIMS, lastly, we provide comprehensive solutions for core electronics domain, talking about covering signal and system modules, SDR, optical fiber communication, and modulation, demodulation techniques through modular and hands-on boards. Talking about Digitode and Qutools collaboration, Digitode is proud to collaborate with Qutools to advance quantum technologies and photonics education across the India academic institutions. Together, we enable hands-on learning in quantum optics and photonics, practical exposure to entanglement, quantum communication, NV centers, and quantum randomness. Support for teaching labs, academic coursewares, and advanced research workflows using real experimental setups and guided learning tools. Now, I would like to introduce our resource person for today's webinar, Slava Tazanova. She has over 5 years of experience and currently working as a product manager at Qtools. Her core expertise lies in experimental quantum physics. We are excited to have her with us today to share practical highlights, insights, and a live demonstration on quantum sensing using NV Center. Topics covered for this webinar, we will be covering second quantum revolution, precision measurement, NV quantum system, applications of sensing, hands-on education, and properties of qubits. Thank you, and handing over to Slava. Over to you, Slava.
Thank you. Thank you, Marinalini, for this introduction. Hello, I'm Slava from Qutools, and I also want to thank to everybody who tuned in today. Today there is a demonstration planned of one of our latest education tools, and before we go to that, I will give a short introduction about our company Qutools and on our efforts to help building a quantum workforce with more hands-on experience. And I will talk a little bit about the physical system of nitrogen vacancy centers in Diamond, and I will show you then how we implemented it in a turnkey setup for education. And because the device is so easy and nice to use, I will try to spend less time on the slides and more time on the demonstration. Our partners from Digitoad Tech said that almost 100 people would attend this webinar, and they would be from with different backgrounds. So I will start with a general introduction. Now I need to share my presentation. Sorry about that. Okay. Let me see. Very well. Okay. So let's start with the general introduction. Last year was the International Year of Quantum Science and Technology, and here in Munich, we are based in Munich, Germany. There was a special event about Bavaria in 100 years, and Chris Monroe showed this graph of human technological progress over time. And the key message for me is that quantum physics is not new to technology. Quantum effects already powered the semiconductor revolution and made the information age from this graph even possible. But what is new today is the level of control. We are now learning how to isolate and manipulate individual quantum systems like single atoms, molecules, and also single photons. And these capabilities are not just scientifically exciting. They will have real impact beyond physics, and they can't succeed through physicists alone. We believe we need engineers, software developers, and many other specialists to turn the quantum platforms into real technologies. And that's why I'm also glad that today the audience is a good mix. So these special quantum systems, the individual quantum system, they can be different kinds. We could separate it in quantum matter and photonics, and the systems have quantum systems have properties like superposition or entanglement, which are these new properties we want to use for the technologies, and we need to control them very well in order to not just make research, but develop technologies. And one very special quantum property is the measurement. And quantum measurement means that every type of interaction with a quantum system changes its state. And that is why no matter which type of system we use, the quantum matter or the photonics systems, we need very precise tools. We need very precise detectors and also alignment tools in order to turn this into technology. And that is where Qutools comes into play. This is a relatively small company, but it has existed already for 20 years. We develop and produce high precision measurement devices. With measurement devices for time, for picosecond, with picosecond resolution, and also with distance measurement devices for picometer displacement measurements. And we also have long experience in the development and production of educational devices for quantum effects. So we fight, so to say, on both fronts of the quantum revolution. On one side, we produce the tools, and on the other side, we educate the workforce. And this very sophisticated devices, I must say. Yeah, I come from, my background is research in fundamental quantum physics, and in Qutools, I see really nice, stable, practical devices. This the development of which is only possible because we have very strong partners. We work together with Enhance to produce highly custom electronics and embedded software for us. And we also work with the MIT, which is made in Turingen. This is where the video comes from. This is our mechanical partner for mechanical design and assembly, and we have a lot of freedom to really adapt the components of this of our products to what we need. So that leaves a lot of space at Qtools for to look for the application and to concentrate on research and development. And herewith I'm ready with the introduction into Qtools and the world of quantum technology that is now developing very quickly these days. And today we will focus on NV centers. With Digitode Technologies, we agreed that we are planning a series of webinars. There will be 3 webinars where also in the following webinars, I will talk about our other educational devices and about our measurement devices. But today we will focus on NV centers. And later on, we'll see that it's actually a pun because you have to focus in order to detect the light emitted from the centers. I will give a very short overview of the physical system because I think that parts of the audience maybe don't know it, and then we'll continue with a fun demonstration. Here next to me are the experiments where you will see the quantum effects happening live. So this is the scary slide, just to show the complexity and the realm of quantum research. These are color centers, different color centers. And I'm not going to go into it, what is what. I just want to emphasize that the nitrogen vacancy centers in Diamond, they're a gift from nature. They're a quantum system that can be worked with, that has quantum properties at room temperature. So it has long enough coherence times at room temperature. We can work with it without ultra high vacuum because it's protected by the diamond lattice. And it has absorption and emission spectrum in the visible range, which makes it really nice to work with let's say non-expensive equipment relatively to the near infrared, for example, where detectors are really difficult to get. And I will not go further into that. It's just how happy we are that this natural quantum system exists. And although here it says that it's an easy quantum system, it is not easy at all. It's a very, very complex system because the NV center, and I hope if you can see my pointer, yes, is in the diamond lattice. It's defect in the diamond lattice. Instead of two carbon atoms in the lattice, there's a nitrogen atom and one empty space, this vacancy. And they build, so to say, kind of a molecule. And this molecule, um, the outer electrons of these molecules are what we would work with, and what the simple quantum system is made of. The electrons have a ground state, and with which is a triplet state, so it has different. It has a 0 and a plus minus 1 spin state. It can be excited with the green light into an excited state. Part of the energy of this green light is dissipates in the diamond lattice, and then the system relaxes again to the ground state and emits red light. This is what we call the NV fluorescence. And now there is this bulb here because this is the bright state. The 0 state typically is being excited and then relaxes rather fast again to the same state and fluoresces in the red. And there is also an option for the electron to relax through a different energy path that we call the dark state. And the MS, so the spin state with +1, plus and minus 1, they have a higher probability to go through this dark state. So that's why here the arrow is thinner. They fluoresce a little bit less. Which we will see very clearly in the experiments later on with the optically detected magnetic resonance experiment. And what else happens when this dark path is chosen is that there is a certain probability that the spin will be flipped from the plus or minus 1 spin state to the 0 state. So what happens is if you shine the green light for a long time, the system will undergo many of these turns, and with a very, very, very high probability, it will end after multiple rounds in the MS0 state. This is a type of initialization or optical pumping that we will also see later on in the system. So this looks very nice. You can explain a lot of core atomic physics properties with it, and it's a beautiful and easy system, especially because it is not you don't need ultra high vacuum for it. These transitions are not narrow line transitions, thanks to the well, thanks in this case, well, because of the lattice, because this is not a free molecule or atom, it's in the diamond lattice. And this makes the system very nice, but it is not the whole story. There are many, many, many levels behind that. There is this lattice behind. The properties of this system depend very much on, as in any quantum system, on the surroundings. There is a big difference. Well, it makes a difference for this quantum system if these carbon atoms are isotope 14 or isotope 13. The NV molecules can detect if they're what the density of other NV molecules is. They can even detect hydrogen impurities in the diamond. They are very, very sensitive, and the transition that we use, or that makes this magnetic sensitivity, is the transition between this MS0 and MS plus minus 1 state. The energy level here is in the microwave spectrum, and one can do spectroscopy with on these levels and see how the energy levels shift depending on the surrounding. So it's a very it is a real quantum system. It is not an easy quantum system, but it's easy to start. But finally, it's a very, very complex quantum system. The I see that there are already questions, but I think we agreed that we will answer them at the end, if that's okay. So what is a typical experimental setup? How does a typical experimental setup work with the NV centers? So there is this diamond, and there are different types of diamond. The NV centers can be naturally part of the diamond. There's a story that, I don't know, one of the biggest of these diamonds was in the crown of Queen Elizabeth. The diamonds with NV centers are slightly pinkish because of the red fluorescence. And so they're natural occurrences of these um, defects. One can also implant them with ion implantation, or one now there are also other types to produce diamonds and NV centers that are called high temperature, high pressure diamonds. And what happens is that the properties of the sample is different. The density of NV is different. The purity of the diamond is different, and all of these factors they affect the properties of the NV center. And one can look at one single NV center with that is an emitter of single photons then, and I will look only at a single molecule, or one can look at an ensemble of these NV centers. And in our setup, we'll be looking at ensembles of NV centers, so a multitude of them. Because it has it's easy, it's better for hands-on education. So what a typical setup has, it has the diamond with the NV centers in it. It has optical setup, an excitation laser that doesn't have to be a laser. That's not that, but a laser is optically cleaner and better to work with. So an excitation laser, then there's the fluorescence in the red light that is again collected typically through the objective. There's a dichroic beam splitter that separates the colors for excitation and detection, and there's a detector and a control unit. And what else is needed is a microwave source and antenna to drive this spin transition between the zero and plus minus state. And next to these simple schematics, this is not a schematic of exactly our setup. This is schematics of a typical NV setup on the left, and on the right you see the setup that we will that we will look at in the demonstration. And again, I clicked because I do not see the setup. It's covered by my Zoom window. I'm sorry for that. And in this setup, we have here through the blue fiber comes the green laser that is reflected here of the beam splitter, the dichroic beam splitter, through the objective onto the sample in here. We have a microwave, high density NV diamond on a microwave antenna that is placed inside of these magnetic field coils that we will use to change the magnetic field and look at the properties of the NV. Then the fluorescence goes in all directions, but part of it is again collected by the objective, goes through the beam splitter and is focused onto a fiber here that collects the light. But what is also very important and will come also in the next webinars and very special about our educational setups is this detector and PC part. Yeah. Here we see again a schematic of the setup that I showed you. We have one fiber for the red light and one for the green light, because we can also detect the excitation light. And the control and detection unit is one standalone device. It has these are different views of the device. So the QEDU, we call it, the education control and detection unit, has 4 photo detector inputs on the back, some cables for to connect to the network or a separate device. And in the front, it has a touch display to work with. One can also connect it to a computer, like I would do right now, and we will work with it from remotely. I'll be standing next to it, but in order to show it to you, I will work from it remotely. And this QEdu control unit is very compact. It's transportable. It has one power cable, so there is only one power cable necessary for the entire unit. Then it connects with a data cable to the optical board, experimental board. This cable, this is the plug here on the QEdu side. One of these control units can control multiple boards, and we will see that next time when I also show you the other setup. So all that is needed, the laser, the microwave generator, the pattern generator, the detectors, is included in these two devices. It's all in there. So this is why this is a rather portable device. And I'm thinking if we should maybe now go to the demonstration, and then I will come back to this slide where once you see the device, you will understand better how what the ideas are in our philosophy about our quantum education devices. I'll do it now in order to just to come back to the motivational slide, that now comes the revolution. We need a broader workforce. That's why it's important to not to only have physicists working with these systems. Physicists, they will be always part of the of this quantum technology, but we also need um, multidisciplinary fields to tackle this complex field. And we want people not to be afraid of quantum effects. Quantum historically is a weird topic, a lot of philosophical discussions about it. But if we want to make it into a technology, there shouldn't be we shouldn't be afraid of it. And that's why we want to build easy to use but also real quantum experiments, because sometimes quantum is unbelievable, and if you need to experience it multiple times in order um, to love it, to believe it, and to be able to work with it. So let me change to the other device. First, I'll change to another camera and show you the device here. Okay, so I'm here. This is my hand. I'm next to the devices. This is what we saw on the one of the last slides, and as far as I can, I will continue with a microphone because then it will be better. And what I want to show you maybe is this is the NV setup. Now you don't see it because there is a laser cover lid. The laser that we use is well, typically works at 10 milliwatt, but can go up to 15 milliwatt. In any case, it's laser, a class 2 or 3 laser, and but thanks to the interlocks we have in the laser safety precautions we have and this lid, you can work without optical without laser safety goggles around it. Okay. And again, the safety is a double. There's a screw on the other side, and I can't lift it up yet, but my colleague will help me now with it. My colleague Santiago, and then I'll lift up the lid. But this is what we saw before, and this is the QEdu that one can operate through this touch screen. And I have here in the back, I have a network cable so that now I can connect through my web browser to the setup. Yes. And that's what I will do now. I will change to my web browser. Let's see. Mhm. There we go. So I have now the same. It might be better to do it like that. No, now it's too big. Okay. Now I have the same edu control unit control software that I can also use directly from the education setup. And what we saw on the we have only 20 minutes. So in short, there are two types of software one can use, one with our devices. And now I'm using this web server based that you can work on the touch screens or have the software for it, or and you can connect with through the web browser to it. And work with the device. There's some introductory home view with what is there. There's the objective. These are the antenna. Here are all the actuators and sensors I have. I have a laser where I can change the mode of the laser. I have a microwave antenna. I'm going very quickly through it because I will show you the different parameters when doing the experiments. We have the magnetic field coils. There's a positioning system for the diamonds because we have three different diamonds. Again, for educational reasons, it's important to see that it doesn't only work with one specific setup. I can go to a different system and I will have similar properties but not identical. And we can have here settings of the pulsed sequences. So what we also see now is that the system tells me interlock is open, laser is off. And this is because we open the lid of the device, and we see we can see here again the setup. So I will lift it up a little bit. So here in the middle is the antenna with the diamonds on top. Here you might be able to see a little bit the objective going in. Here are the fibers, and it's all. I don't need to align anything. It arrives like this in a box. I with the lid on. The only thing I need to connect are the optical is one optical fiber, then the data cable that goes to the QEDU, and then I can with the experiment. I need to share again with you. Yes. Okay. So my in this first view, one can choose a diamond to work with. We prepared it. I will show you maybe later if there is time how to do the scan, but it takes maybe 1 or 2 minutes, and now we have a good position at the saved position number 3 that we chose. It's a nice position of the confocal optical setup. Of this I didn't mention, but the optical setup is confocal so that we can have only signal from a possibly single point of the diamond in order not to have inhomogeneous signals that we need later, because the green excitation, the microwave, and the magnetic field have to be as homogeneous as possible if you work with a nitrogen vacancy ensemble, so that you have a clean signal. Then I showed you here where the different settings. And here on top are experiments, are guided experiments to go step by step. You turn on the device, you can go to the first experiment, find a diamond. I find a diamond. Here you can load some presets. Then we go to the next experiment, which is about learning about how the device works with the pulses that we need. And the first experiment I will do will be to show you why we need the pulses. I told you in the energy level scheme that we need the green light to in order for the NV center to fluoresce. And we also do the preparation of the system with it. So in the typical experiments, there'll be one green pulse as a preparation pulse and another green pulse as a detection pulse. And this is a schematics of what the machine in the pattern generation in the control unit tells the device to do. Go with one green pulse, then do some microwave excitation and detect, for example. And we see also here this purple view is what we can detect simultaneously. So here I see the red fluorescence to what I told as I should do. And I think here I can, for example, tell the second laser pulse to start later. Yes. Okay. It's because I'm online and I'm showing now there's a slight delay, I think because of the webinar, but typically it's instantaneous. So I you set the and you set the timing and directly you can see what is happening to the device. And in the first exercise that or the first experiment that follows, we will do the T1 relaxation experiment. That means we will excite with one laser pulse the second laser pulse, and we will change with time the detection of the second pulse. I see I don't have good internet connection. It's probably because I'm connecting to the device and to the server. So maybe we can, maybe, yeah, thanks. Sorry, my colleague will look for a cable. So here we are. I will again load some presets. It says we're not going to use the CW. We will do the pulsing. I will press the play button. That would load now. That will load the presets and. Mm, it takes a while. I think it's also because I'm a bit hitting the table. It's not an optical table, it's just a normal um, normal table. I might have changed a parameter before that. This is not what we expect to see though. Let me check also in the real device if this is what is happening. Yeah. Yeah, it's because of the connection. We'll try it now in a different way. Because it's too much data. It's my computer is the problem. The device that is exactly next to me. Sorry about that. About this technical issue. Mm, okay, no. Okay. You know what well, maybe. Do you see the the measurement I see and that we're supposed to do? So we have on the x-axis, we have the delay of the second laser pulse in microseconds. So you see it goes up to 2 milliseconds the entire time. And we see that on the y-axis is the intensity of the fluorescence. We detect when the second pulse arrives. So I have one excitation pulse. That means I pump my system in the MS0 state. Here we have also in the QEDU, we have a little manual with the help with this electronic scheme that we saw before. So we pump with the green light the system, it ends up in the MS0 state, and then we wait for some time and we see is it still as bright as after the end of the optical pumping. And in the beginning, yes, it is bright, but with time, about let's say two milliseconds, it's actually about 3 milliseconds, it goes the signal goes down, and this is the thermal relaxation of the spin system without optical pumping. Because it's not an isolated system, it relaxes again into both spin states, and it doesn't shine as bright. So this is one property we saw, and now we will go to the NV sensor, to the optical detected magnetic resonance. Now I'm wondering, maybe somebody from Digitoad can tell me if the transmission is nice and if you can see the signal also that I'm looking at, like this magnetometry plot, and if it changes fast enough, because I have not much feedback. Okay, I'll just continue and I hope you see what I see.
Perfect.
Okay. Good. Okay, so now we're at the optically detected magnetic resonance. I can here are the different views I have, and I can for example, yeah, this we saw before. Now I have a long excitation pulse, I have a microwave pulse in between, and I have a detection pulse. And in this detection pulse, I have a detection window also that I can change. And now I do multiple of these shots, and every time I change the microwave frequency. This is the experiment that is being done here. And here we see on the x-axis is the microwave frequency, and this is this resonance. They're around 2.8 gigahertz. There's the resonance of the NV center. And in theory, we would expect only one peak. There should be one peak, because without, let's say, magnetic field or electrical fields or other fields that would split the energy between the plus and minus 1 ms states, they should be at the same energy. But we see they're already splitted, and this is not the Earth magnetic field. This is another effect that the NV center can sense. It's the stress in the diamond. So it's type of a of an electrical field. It's a stress in the diamond that already at zero field splits the two peaks. And the what we will do now is or maybe I will first zoom in. Here I will choose a region, a smaller region here how much time do I have? I don't have much time. Okay. um, I will just show you this, that there's also a thermal dependence on the resonance. The resonance here in the middle should be at 2.87 in theory, but we see a lower the resonance is at a lower point. And if I reduce the power of the laser by some percentage, you will see that this resonance shifted. Yeah, it was lower, and this shift is due to temperature, because the NV sensor is also sensitive to temperature. The entire resonance frequency shifts with temperature. I'm going to put the cursor here. Yeah, to remember where we were, and I will again increase the laser power. And it's because we sense so much laser power. The diamond has a very high thermal dissipation, but still it heats the diamond, and you see that the resonance shifts. And this is happening here in front of us. Okay, so it's a real system. This we really want to emphasize on. I'm going to remove that, and because we don't have so much time, because I was talking too much. I will show you now the the dependence on magnetic field of this resonance. So there is the Zeeman effect, a typical atomic physics effect that the energy levels split with magnetic field. And here we have magnetic field coils through which we can send a current. You see the change happens slowly because we average. I'm sorry, because we average. If I do not average, this is the signal I would get real, like this is one shot without averaging. This is already a pretty good signal, I must say. Yeah. It also, if I bang on the table, it would do this. It's mostly because the positioning changes a little bit, but again, it shows it's a real system. So without averaging, I will change the field quickly and tried to find eight different peaks. And now you ask, why eight peaks? We had two. And this is because the NV the NV centers are oriented along the, the axis of the diamond lattice, and there are four different orientations. And the magnetic field I have, it projects along each of these orientations, and this is how the different NV center sends a different magnetic field. So I could also have a magnetic field where the projection is identical in all directions. I have not checked which magnetic field it is in this case. But right now we see, so here is the middle at 2.87. Maybe I can put the cursors there just to see, for you to see and on both sides, of course, symmetrical is are the MS -1 and the MS +1 states are going there. We don't see the entire spectrum. Yeah, now we see a little bit more. So here I have one NV direction. Here I have two overlapping, and here I have one single one. And because I wanna be able to cover also another very nice experiment, I will go now here to this single frequency of the MS01. I will go to this, and I will choose now this frequency. I will say go to this frequency, and I'm going to go to the next experiment, just to show you what we can do here live with our experiments. So what is happening here? I'm going to show you again the schematics to explain. We have the green laser always on, so we're always pumping, and we're looking the graph that we see is this purple region, and after 2 microsecond, we turn on microwave pulse at the resonance. We chose the resonance before, and we use a microwave pulse of 3 microseconds here. And what we see is we have this high fluorescence. The laser is always on. We turn the microwave on, and it goes down the fluorescence. The microwave is still on until here, but here we see oscillations. And these oscillations, this is a typical quantum mechanical property. This is what is called Rabi oscillations. Here, not a very clean measurement because the laser is always on, but this is the same effect behind Rabi oscillations. There's an oscillation between the two levels, the -1 and the 0 level, and it oscillates with a given frequency. There is also a decay, a decoherence, and then here, around here, the microwave pulse, we stop it, and we see here slowly the optical pumping again to the 0 state. What is also very nice, if I reduce the power of the microwave, please now look at the frequency of these oscillations. If I reduce the power of the microwave, the oscillation has a higher frequency. This is also a direct typical effect from the Rabi oscillations. And if I don't have enough power of the microwave, I can't. The effect is not so strong. So also this peak is not so strong. Yeah. And also, and another nice trick is that if I go off resonance, again. So I had now this frequency on resonance. If I go off resonance, it will also change. So maybe I'll hit now another resonance. I don't. Yeah, I think now we hit another resonance just by changing the frequency. One of the other peaks that we had before. So this is one of my favorite experiments, and now I think we were somewhere here, and there is something else I want to show you. So we were looking at this effect. We're looking real time. There are no we are this is not a sequence. We're looking here at the signal of the photodiode in these 10 microseconds. We can do that with our control and detection unit. What I want to do now is I want to increase here the region that we look at. No, I want to go here. I want to go to after the pulse. So now I will also see what happens when the laser pulse is off. Now we look at the larger window. You see laser, the green laser is on, and here at the end, the green laser is off, and I have almost no signal at all. And here, maybe you see the little oscillations here on top. This is it. This is really the difference between the MS levels. This is the quantum mechanical signal that we get, the quantum mechanical signal that will be used in the NV center as a magnetic field sensor, as an electric field sensor, as a temperature sensor. This is a very, very, very small, a few percentage difference in fluorescence. And I think I should stop so we have more time for the questions. And I can also show you Rabi oscillations, but we saw that it works. So maybe it's time for the questions. What do you think, Brinalini?
Yeah, Slava. So now you can please type your questions in the comment box and we will be replying into it.
Maybe my colleague already started. Okay, but or maybe just yeah. I want to remind you again for the philosophy. So there's a control unit. There's a ready to use setup. You have, and we give these guided experiments where you can just load presets, but you can do every experiment on your own. And we have also two types of software. We have these easy to use software, and there's also Python based software where from a remote computer you can control our hardware the way you want. And we're doing this in an open source manner so that you can exchange with educators from around the world. And now we'll check. So there is an audio lag. Okay. Why do NV color centers maintain coherence for a long time? Nature made them such. I don't know. This is not a some they're not very well isolated. These are yeah, it's not something we can really control. What affects the sensitivity of NV centers in diamond? Well, the quality, the purity of the system. How, for example, what do you mean the sensitivity? How well? There's the diamond properties itself, like how clean is your diamond. There's a question of Ravi. What affects the sensitivity of NV centers? There's the quality of the diamond, and of course also the quality of the entire setup. Okay, you can do CW measurements. CW measurements are when the laser and the microwave are on at the same time, and there you can do only DC fields. You can also work with pulsed experiments, and you can detect AC fields, changing fields. You have higher sensitivity with pulsed experiments. Because of these oscillations, you can do experiments that are called spin echo, where you use a pi pulse in between your measurement to clean the noise and stuff like that. So pulsed experiments give higher sensitivity. Homogeneity of everything, of excitation light, of magnetic field, of microwave field, everything affects. It's a quantum system. Everything affects the system. What do we have? Are the building fundamentals of quantum system different than of a quantum computer? I'm not sure mm, what this means. A quantum computer uses simple quantum systems, so it uses two-level quantum systems as qubits, and the quantum computer is not does not go into sensing or into using the quantum properties directly to sense the environment. It is supposed to be as um, secured from the environment as possible. It works mainly with these superposition, and entanglement properties, quantum properties. There is the digital quantum computer tries to make bits of information from two-level quantum system. Very difficult. We can't clearly see the slides. That I'm sorry. What is the signal to noise in the Rouge? Signal to noise and the resolution value for our setup. Well, signal to noise depends very much on the parameters you have. You can you saw me changing from no averaging and averaging. We have a rather good contrast of around 2% between the two spin levels. You saw this last measurement where I showed you this is the fluorescence with the light on and fluorescence without light, with light off. I mean, no fluorescence with light off, and these little ripples on top. So this I find very nice that we see it. I could maybe try to show you if you want. Um, we can do also demonstrations if you contact us or you contact Digital Technologies if you have a specific question for if this is the right system for you to purchase for your education lab or research lab. We can do a separate meeting too. But we have I would say rather good signal to noise ratio. The T2 time is not great. I don't have a number now because we have these high temperature, high pressure diamonds. So we have a high density NVs, and it depends from diamond to diamond. We don't pre-select the diamonds. You have 3 diamonds. Some are great, some are better than the others. They're just yeah. How can I check the electric effect? With the electric field, we don't have an implemented sensor or let's say parameter or actuator for the electric field. And I think you need very strong electric fields. And then I would say do not use our device because everything is very compact and there's also the laser diode inside this box and everything. So maybe do not apply very strong electric fields to this setup. Um, what is the frequency resolution of the microwave pulses? We can go down to, I'm not sure if it's 2 kilohertz, something like, let's say 2 kilohertz. But that's already too, yeah. Uh, Minimum value of magnetic field that can be detected. I don't know. We are not. We haven't checked. We haven't checked because we do not use it as sensor. I mean, in the view that I showed you, you need the maximum values we have here are we go up to 15 Gauss, I think 15 Gauss. We go up to 15 Gauss, and you already see an effect at maybe around 1 Gauss, but you see the effect of really, like, you see it in this large frequency spectrum. Now, typically, if you want to detect small values, so if you use NV as a sensor, you have a bias field. You have already a field that you know, a known field, maybe from a permanent magnet or something, and then you detect the changes, because then you already will have this split. You with the bias field, it will be best if you actually split the directions, the peaks with the four orientations of the diamond, and then you have four sensors simultaneously. um, I'm not sure what the efficiency is meant of the system, but maybe something to tell you: we are now working only with fluorescence. We're not looking at the contrast. In a typical post experiment, or like in a scientific post experiment, you would always compare in one shot. So you do the preparation pulse, and then you do the detection pulse. You will compare the beginning of the detection pulse, where comes the interesting signal from the NV and from what happened in between preparation and detection, to the end of the preparation pulse. So the end of the preparation pulse is how you prepared your system. It has this fluorescence. Then you do something with it, microwave pulse, or you let time evolve, or multiple microwave pulses, and then you detect. And typically you compare these two, and this is called contrast. And the contrast, of course, delivers a cleaner signal. We have a very clean signal just by checking just by using the fluorescence. And in the next software, this is a rather new device, and in the one of the next software issues, there will be also the option to compare between only fluorescence and between contrast. This is not implemented yet. If you use the Python version, you can do it yourself already now. The time duration for which each fluorescence data point is read. I'm not sure what you mean. It's the pattern or like the control unit. Is it 200? 200? We have a 200 megahertz FPGA running the system. So we get the signal instantaneously. Like we can we 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 look. I think the shortest sequence we can have is one microsecond. 1 microsecond, but the 1 microsecond is not enough with the uh, yeah, for the laser power to start the sequence. I'm curious to know the cost of the kit. The cost, we discussed with Digitoad that we will not tell you in the webinar, but you can contact Digitoad Technologies or us, and we can send you a quote, or we can have a meeting for a discussion. How you can purchase this unit for teaching is you contact us, and then the delivery time is typically shorter than the administrative the time for the administration to do it, but let's say it's about 2 months, 6 to 10 weeks. Yeah. um How come the NV is able to interact with the microwaves and bring resonance closely? I'm not sure what the question is. The microwave antenna we have is in the middle of the um, coils. In the diamonds are glued. Maybe I can show you here. Let me see if I change the video camera. Okay, that's not great. So here is a scan. Here is a scan, or a 2D scan of the positioning with the three diamonds. And Yeah, with the camera is also not nice. So what we see here is actually here we have one diamond, here we have another diamond, and here we have a third diamond. And it doesn't look like a big bright diamond. You see only the side of it. It's because this is a confocal image. So if you change the Z, like the position of the objective, you will see a different piece of the diamond. This is, of course, you can't really do cuts like in CT imaging because at some point the you're too deep in the diamond and the light just doesn't enter, or sometimes it just reflects off the diamond surface. That can happen. Um, and these diamonds, so this is 2.3 millimeter to 3 millimeter. So they're placed in in a diameter of 1 millimeter. So they're about 100 micron large diamonds, 150 micron large diamonds, and three of them are placed in a diameter of 1 millimeter next to each other. And then these diamonds are they're placed on a small glass microscopic plate, and they're glued onto the microwave antenna so that they have the highest possible microwave field, and the microwave antenna is here here in the middle of the coils. So this is how we get this strong microwave signal, and homogeneous. It's they're in a plane and things like that. We put a lot of thought in that, and we have also nice really professional collaborators. We have a research project with Fedor Ilecko from the University of Ulm and with Adam Gali from the research center in Budapest. And we're really happy to collaborate with them and ask lots of questions. We were, for example, very um, um, worried when we saw this shift in resonance with the laser power. We were like, "What's happening?" And we we saw it actually in the different conditions, and then these professors explained us that it's temperature, which is nice. We have a real system, and the engineers building it didn't know what it can do. Um, is there any beginner's course to begin with for undergraduate students? We provide a manual with these easy to go with experiments. You don't need to really know that, but we don't have, it's very, very basic theory that is written in the manual. Because our experience that we have already for some decades is that every educator has their own approach, and it depends if you use the device to go maybe more in the sensing direction or to go in the qubit direction. And if you want to go in the qubit direction, you'll be, yeah, it's a different approach. So we don't have a ready course, but we expect with these open source software, Python-based open source software, for people to connect with each other, to see, I'm using this, you're using this, maybe can we share? Good. Is there? Okay, Anoop, I
Us.
see he's there. I think because the time is because the
Um,
time
yes,
yeah.
I think we should answer these questions, but we can revert to all of you. Those questions which have not been answered, we can take them up and respond to you over the phone or via email, because it's almost going to be 4:15. But I really thank, we had great participation here, and I really appreciate your interest in being a part of this webinar. Also, we're going to be doing a series of it, some with Slava, some with other partners as well. And I've dropped in a comment with a link to a survey. So if you can take that, I like your responses to that to see how we can make our webinars even better. Also, I would like to tell all of you that we are aligned with ASIT, and if you are looking to build a curriculum either for undergraduate courses or postgraduate courses, Digitrode can help you with that as well. So we have also mapped QUtool solutions with the experiments that are a part of AICTE curriculum. So if you have any questions on how you can adopt these solutions to the curriculum approved by AICTE and which are in tune with National Quantum Mission, we'll be glad to help. Drop us an email or give us a call and visit our website, drop an inquiry, and we'll get back to you within 24 hours with expert guidance. And if you need technical assistance as well, we can get in touch with you, or bring in Slava to answer the questions and work with you to get this implemented in your institute. All right. Once again, a big thank you for everyone for being active participants, and we'll probably see you in the next webinar. Thank you, everyone.
Thank you all. Bye.
Thank you, Slava. Thank you, Santiago. Thank you, Anup. And thank you all.
Thank you. Bye bye. Thank you for having us. Bye bye. Ciao.